Hi everyone, in this video we are going to do some Lagrangian mechanics. Specifically, we are going to be taking a look at the system I've sketched out here and solving for the general time evolution of this system. So what the system is, it's a pendulum, but the support or the pivot of the pendulum is free to move along a horizontal line. So you can imagine that this bit at the top here is some sort of block with a hole drilled all the way through the middle of it, which is free to slide backwards and forwards along a pole. Or equivalently, you could imagine it as like a trolley with some wheels, which is moving horizontally along a surface, but just some kind of massive object which is free to move. That's the support of the pendulum. And as I've written there, it has a mass of m1. The other parameters of the problem are m2, just the mass of the bob at the end of the pendulum, and L, which is the usual length of the pendulum. So M1, M2, and L are the fixed parameters of the problem. What we're trying to solve for is the time evolution of our two generalized coordinates that we're describing the system in terms of. Firstly, you've got the standard angle theta, just the angle that the pendulum makes with the vertical. And for this problem, you've also got a generalized coordinate x, which is the horizontal displacement of the support of the pendulum from some arbitrary reference position. It doesn't really matter where we take x equals 0 to be, as we'll see later on, but it's just the horizontal displacement of that top bit of the pendulum. So let's start working through this. And of course, the first thing I'm going to write down is just a reminder that the Lagrangian is T minus V, the kinetic energy minus the potential energy. And we want to express L in terms of small l, the length of the pendulum, and theta, so that we can get some equations of motion. And what's often a useful first step in problems like this is to write down expressions for the Cartesian coordinates of all the objects in your system in terms of the generalized coordinates that you're ultimately wanting to work with, simply because that tends to just make it easy to come up with expressions for both t and v. Now the coordinates, Cartesian coordinates of the sliding support of the pendulum up at the top, mass m1, are straightforward because, well, by definition, its x coordinate is just x. If we define the y coordinate in the usual way, just pointing upwards from our arbitrary reference point, then the y coordinate of the support of the pendulum is always going to be 0 because it's constrained to move purely horizontally. So we don't really need to write down new expressions for the coordinates of the support. But what about for the bob of the pendulum, which is moving around in a more complicated way? Well, if we call the coordinates of the bob x2 and y2, so write down expressions for those. X2, well, you've got your horizontal displacement of x, right? Because this support is already at a horizontal displacement of x. But then you've got this extra horizontal displacement here from the dashed vertical line to the bob itself. And using trigonometry, you can see that that horizontal bit there is just L sine theta. So the overall x coordinate of the bob is going to be x plus L sine theta. What about the y coordinate? Well, we basically just need to know this vertical displacement here. And we're going to make that negative, right? As we said, we defined y in the usual way to be pointing upwards. Our bob is always going to be hanging below, well, not necessarily always, but later on we're going to focus on small oscillations. But certainly in the configuration that I've drawn here, we expect y to be negative. The vertical line, this one here that I've just marked on, again, trigonometry, that is L cos theta, and therefore our y coordinate is going to be minus L cos theta. Now, that's going to be helpful for the potential energy. For the kinetic energy, we of course need the time derivatives of those, so let's just write those down as well. x2 dot time derivative of x2 is simply x dot plus, and then using the chain rule, you've got L theta dot cos theta, and then y2, again using the chain rule, is going to be L theta dot sine theta. You lose the minus sign because cos differentiates to minus sine. So now let's start constructing our Lagrangian in terms of our generalized coordinates. And let's do the kinetic term t first. The easiest bit of that term is you're going to have a half m1 x dot squared for the kinetic energy due to the horizontal motion of the support. Then you're also going to have half m2 times x2 dot squared plus y2 dot squared, kinetic energy due to the two-dimensional motion of the pendulum bob. So let's factor out the half m2. We need to square all of this, so x2 dot squared. That's going to give you a couple of terms. You're going to get an x dot squared term. You'll get your cross term, which is 2. Well, let's put the L first. 2L x dot theta dot cos theta. Then you'll get the term where the trig bit is squared, so L squared theta dot squared cos squared theta. You also need your half m2 y dot squared bit, so we're just going to square that, add that on, which is going to give you L squared theta dot squared sine squared theta. What simplifications can we make with this? I'm going to regroup the terms a little bit first, because you've got an x2, sorry, just an x dot squared there and an x dot squared there as well. We can group those together and have half m1 plus m2 x dot squared. Then what else are we going to have? So this 2 here will cancel with that half if we expand the brackets, and you will get m2l x dot theta dot cos theta. And then something nice happens with these final 2 terms, because you've got cos squared theta plus sine squared theta. If you factor those last 2 terms together, cos squared plus sine squared is 1. So those 2 terms join, become one term, which when we expand the brackets is just half m2 L squared theta dot squared. How about the potential energy V? Well, the only potential energy in this system is going to be gravitational potential energy. And we don't even really have to think about the gravitational potential energy contributed by the support of the pendulum, because it's not moving vertically. And with gravitational potential energy, the only thing that matters is changes, right? And we're always free to define our potential energy up to a constant. So we may as well just ignore the gravitational potential energy due to the support moving horizontally. And for the bob, you've just got your mgh term m2g y2 for gravitational potential energy. We've already got our expression for y2 down there, which includes the minus sign. So this becomes minus m2 gl cos theta. So we've basically taken our 0 reference point for gravitational potential energy to be the vertical level of the support. So the first term in L is an x dot term. So why don't we start by finding dl by dx dot. So that first term is easy to differentiate because m1 and m2 are constants. Just differentiate that and you're going to pull down a factor of 2 and get m1 plus m2 x dot. This second term, differentiate with respect to x dot, you just get rid of the x dot, so it's m2l theta dot cos theta. There is no x dot dependence in the final 2 terms, so that's our first derivative completed. Even easier than that, in fact, is dl by dx itself, because there's no explicit x dependence in the Lagrangian, so that is just 0. And by the way, if you're familiar with Noether's theorem, you'll immediately recognize that dl by dx being 0 implies that there's a conserved quantity. The conserved quantity here is this stuff, which is just the linear momentum in the x direction. But anyway, let's find our other derivatives, the theta derivatives. So dl by d theta dot first, go through term by term. So first term that has theta dot dependence is the second term in L. If we just differentiate that with respect to theta dot, you are going to get m2l x dot. Theta dot disappears, but you've still got your cos theta. Again, that term there, you've just got theta dot squared. So pull down a factor of 2 when you differentiate and get m2 l squared theta dot. And that's it. So let's just find dl by d theta, and then we'll be done with this differentiation. No theta dependence in the first term. Second term has a cos theta that differentiates to minus sine theta. So you get minus m2l x dot theta dot sine theta. No theta dependence there. This term again differentiates to minus sine theta. So you've got minus m2 gl sine theta. So I've just kept a summary of the key information up at the top of the screen there, Lagrangian and its derivatives. We can now put all this together to construct the equations of motion. So if we write down the Euler-Lagrange equation for generalized coordinate x, we've got d by dt of dl by dx dot minus dl by dx is equal to 0. We just look back up there and plug in the derivatives. So we are going to be differentiating this whole thing with respect to time. So your first term gets a double dot, right, because it was already x dot. Now it's going to be m1 plus m2 x double dot. Then I guess we're going to have to use the product rule to differentiate second term in dl by dx dot with respect to time. So you're going to firstly get m2 l theta double dot cos theta when we differentiate the theta dot but leave the cos theta alone. Then you're going to, for your next term, leave the theta dot alone, differentiate cos theta with respect to time. Cos becomes minus sine, so you're going to have minus m2l theta dot sine theta, but then you get another theta dot from the chain rule, so this becomes theta dot squared. And all of that is just 0 because remember dl by dx is 0. So there's our first equation of motion. Let's go through the same procedure for the theta equation. So d by dt of dl by d theta dot minus dl by d theta is also 0, just Euler-Lagrange equation. So first step is going to be differentiate all of this with respect to time. Again, for the first term there, we're going to have to use the product rule. So we're going to get an m2l x double dot cos theta when we differentiate the x dot bit. Then we're going to get a minus m2l x dot theta dot sine theta when we differentiate the cos theta part. Second term is easier to differentiate because there's only one bit that's time dependent, which is the theta dot. Differentiate that, we get m2l squared theta double dot. Then we have to do minus dl by d theta, which just means we're subtracting all of that stuff that I just underlined. Subtracting meaning we switch the minus signs into plus signs, so we are going to be adding on m2l x dot theta dot sine theta, and also adding on m2gl sine theta, and then we're going to set that whole thing to 0. Something nice happens because you'll notice that this term is actually the same as this term with opposite sign, and so we can just cross those out. Those cancel. We can also divide everything by m2 and in fact by l as well. So if we divide through by m2l, then we get a simplified equation which looks like this: x double dot cos theta plus l theta dot came from that term there, and then finally we've got plus g sine theta is equal to 0. So here is our complete set of two coupled differential equations for x and theta that govern the motion of the system. There are, of course, non-linearities in there. You've got squared derivatives, you've got sines and cosines. I'm pretty sure we're not going to be solving those exactly analytically. So let's do what we usually do and make an approximation. Let's look at small oscillations and consider what happens when theta is much less than 1. And so, well, let's just rewrite our equations of motion. The first term of the first equation doesn't change because it just involves x, so m1 plus m2 x double dot. Now, let's use a small angle approximation for cos theta. This cos theta here, it's roughly 1 minus theta squared over 2. If we want to get linear equations of motion, we only want to work two terms up to first order in theta and its derivatives. If we include the minus theta squared over 2 bit, it's actually going to be a third order term because you'll have theta double dot times theta squared over 2. So we just approximate cos theta as roughly 1 for the purpose of this term, and say that that's roughly just m2l theta double dot. We can already ignore that third term because you've already got a second order bit there. If we did the small angle approximation with sine theta, it would become a third order term because sine theta is roughly theta. So you would have theta dot squared theta, definitely a higher order than we want to be considering here. So here is our linearized first equation of motion. That's roughly 0. Let's call that equation of motion 1. Similarly for the second equation, let's just say cos theta is roughly 1. So first term becomes x double dot from there. Second term doesn't change, so L theta double dot. Third term is going to be roughly g theta. and that's roughly 0. So we've got two much nicer looking linearized equations there. And there are probably various ways to solve this. I think the most straightforward way is to notice that equation 1 allows you to express x double dot in terms of theta double dot. So we could rearrange equation 1 and then substitute x double dot into equation 2, and we would have a second order differential equation purely involving theta that we could then solve. So if we do that rearrangement of equation 1, we conclude that x double dot is roughly minus m2l over m1 plus m2 times theta double dot. Then we can go ahead and substitute that into equation 2, and so our x double dot term there is already all of this stuff. I'm going to join those first two terms together because they both are proportional to L theta double dot. So I'm going to have minus m2 over m1 plus m2 from that bit there. Then I'm going to have plus 1, the plus 1 coming from factoring that second term, and then I factored out an L theta double dot like that. And then we've still got our plus g theta sitting there at the end. So this is nice because it's basically just a simple harmonic motion equation for theta. To make that even more obvious, let's rewrite that in the standard form for the SHM equation of motion, where we want to have theta double dot plus omega squared theta is roughly 0. So we're basically dividing through by that bracketed term and by L. The bracketed term itself, if you add 1 to the fraction, you are going to get m1 over m1 plus m2. So if we then divide through by that, you're going to get theta double dot plus, well, you've got g over L, and then you're going to have m1 plus m2 over m1. So by dividing by that fraction that we were talking about, that times theta is roughly 0. So what's the solution to this? Well, it's just your standard SHM solution. You can express it in whatever form you prefer. I'm going to write it as theta is theta naught cos of omega t plus phi. Theta naught and phi are arbitrary constants. The amplitude of the oscillations of theta and the phase of the oscillations to be determined by initial conditions. And this omega here from your standard SHM equation is given by omega squared equals coefficient of theta, which is this g over L times m1 plus m2 over m1. Finally, let's figure out how x varies now that we know how theta varies. Then we'll do some physical interpretation of our solution at the end. So we should go back to this relation here. That tells us how the x acceleration compares with the theta acceleration. Now that we know what theta is, we just sub that back into theta double dot there. Then we can integrate a couple of times to find how x itself behaves. So x double dot is going to be, well, I'm going to start by writing down this prefactor, the m2l over m1 plus m2. What about the theta double dot bit? Well, when we differentiate this twice, you just pull out a factor of minus omega squared. So the minus cancels with this minus up here, whole thing becomes positive. You also get a factor of omega squared at the beginning. So it's that times theta naught cos of omega t plus phi. Then we can integrate that firstly to get x dot. So integrate once with respect to time. That's going to make your cosine become a sine. You also have to divide by this omega by thinking about the chain rule. So your omega squared here becomes just omega. You get omega m2l over m1 plus m2 times theta naught sine of omega t plus phi. It would be easy to forget, but make sure we have a constant of integration there as well. I'm going to just call it alpha. Then we just have to integrate once more to find how x itself behaves. This sine term is going to integrate to minus cos. You'll also have to divide by this omega from the chain rule, so that makes this omega disappear. You end up with minus m2l over m1 plus m2 theta naught cos of omega t plus phi. Integrate alpha with respect to time, you get alpha t. Then you need another constant of integration, which of course I'm going to call beta. So we have here our general solution for x. and up here was our general solution for theta. So to finish off, let's just take a moment to think physically about the meaning of the solutions that we've got, try to get some understanding as to what's going on here. The first comment I want to make is that this minus sign here means that the oscillations in x are always in antiphase with the oscillations in theta, right? Because they're both proportional to cos omega t plus phi, but they always differ by that minus sign. That makes physical sense. We can understand that from the fact that linear momentum in the x direction is conserved, right? If the support of the pendulum lamp at the top moves one way, then the bob has to move the other way so that the center of mass of the system doesn't move overall. Otherwise, momentum would not be conserved. Another thing that's often interesting to do is to take limits of your solutions. In particular, look at this omega squared here, and imagine what would happen if m1 were extremely large. The reason for imagining that is that, well, if m1 is extremely large, then it's basically not going to move, right? If it has loads of inertia, it's going to remain essentially stationary, and so we would expect our solution to reduce to the sort of standard solution for just a pendulum with a fixed support, right? So if we take m1 to infinity, the numerator here is roughly just m1. That will then cancel with the denominator. You get omega squared is equal to g over L, which is indeed the natural frequency of oscillations of a simple pendulum. And similarly, in that same limit, as m1 goes to infinity, because m1 is on the denominator of your x solution here, the oscillations, the amplitude of oscillations in x goes to 0, which just tells us that the support doesn't move in the limit when it is extremely heavy. This is all consistent with what we would conclude when we just have a simple pendulum. Final thing I want to talk about is this alpha t plus beta term, which is present in the solution for x, but not in the solution for theta. Right, so theta is always just oscillating backwards and forwards. X has this extra bit. If you think about it, that just represents, well, alpha t is like a constant velocity motion. It's just like distance equals speed times time. So alpha is like a linear speed, and beta is just an offset. I think I mentioned at the very beginning that where we choose our origin for x, like a reference point for x equals 0, it doesn't matter. The reason for that is that you've got this plus beta in your solution anyway, right? So it's an arbitrary offset, so we're free to choose where we measure x from in the first place. And so overall, this alpha t plus beta just represents like a linear motion and a constant offset of the motion of the system as a whole. That's still consistent with momentum being conserved because that component of the motion is always there. It doesn't change, right? If the whole system is moving to the right with some speed, some initial speed, then it doesn't change its speed. Of course, it would always be possible to do a Galilean transformation into an inertial frame co-moving with the center of mass of the system to make that term disappear so that the motion is purely oscillatory. So that's basically all for this video. Next time, the plan is to look at a very similar system where you have a pendulum with a sliding support, except instead of allowing the support to slide freely, we're going to force it to oscillate backwards and forwards with simple harmonic motion and see how that affects the way that the bob moves. So thanks for watching and hope to see you soon for that next video.